Hello. How's everyone doing? Ready for the midterm tomorrow? Getting enough sleep? No one's saying anything. Okay. All right. So today's just going to be a review, right, for the midterm. So you're supposed to ask me questions. You want me to go over some material a little more carefully, something we did in class, or if you didn't understand a homework solution, we can go over that. So let's see. Anyone has a question? If you don't have any questions, we're not going to have a review session. So the point of the review session is to go over the material that you may have some questions, doubts about. So.
For lecture 18.
Can you guys hear me? Say yes or no, at least to that.
We can hear you.
Yes.
Yes?
Yes.
Uh-oh, I'm not able to hear people. Okay, say something.
Yes, we can hear you.
Okay. All right. Okay, so let's see. I know there were some questions about on Piazza about the midterm that I posted, the practice midterm. So from spring 2017, this was, as I mentioned before in class, this is the first time I'm teaching 490. So I didn't have any of my own previous exams to give out to you guys to look at, so to practice. So this was the closest one in terms of content to what I'm teaching. So I gave you, I put this up. I mean, I put a midterm one as well before from the same semester, spring 2017. Well, the problem is that the solutions the solutions that are written down, this was, I think, solutions prepared by Professor Srikanth. They're not necessary. They may be a little confusing to you guys, and there were some typos and some notation issues and so on. So, for example, in this question, I think it would have been better to use a different symbol for the Lagrange multiplier here rather than using lambda. Although it turns out that the Lagrange multiplier turns out to be the eigenvalue, so maybe it was okay, but it's still a little confusing because lambda you will need to show that lambda is an eigenvalue of Q, and lambda maximizes this. Lambda I maximizes this. So but other than that, I think it's fine. Let me see if there's any other issues with this. Any questions about this question?
I just have a quick question. Beneath line 1, where you multiply on the left by x transpose, what happens with the x in the lambda x side of the equation?
X. Oh yeah, so the constraint is that x squared is equal to 1. Right?
Oh, gotcha. Okay, thank you.
That's why it goes away. Yeah, I think there was there might have been another typo here. Let's see. No, I think that's fine. F2x. Yeah. Anyway, so the other thing is that if strictly speaking, you need to check that the solution that satisfies the first order conditions is actually the minimum of minus x transpose qx. So you need to either use general sufficiency or use the second order conditions to check that, which they didn't do in this question. So it's kind of assumed that the first order conditions give you the maximum. Okay, so I'll probably not let you do that. I want to ask you a question like this where it may be hard to check those conditions anyway, but I wouldn't. Yeah, so that's thing. Let's see. Yeah, this second question was actually in you had a version of this in, or some form of this in homework 4, I think. So you saw this before. And actually a version of the third problem also, slightly different form setting, but it's essentially the same kind of steps that you should have seen in homework 4. And the last question, yeah, so this one was a little bit, this is probably the most challenging question on this exam. It might have been a little confusing. So, because here, assuming this latest condition of strong duality holds, you basically can conclude that L is the Lagrangian is a convex function, and you need that in one of the steps, I think, which is not completely specified. So, again, all right. So this was just this is the best sample I could give you. Okay, so maybe a better a better model for the quiz will be the homework questions. Okay, the quiz will be very similar to the homework questions that you've seen, and they'll not be as involved as the homework questions, in the sense that you may not there'll be simpler versions of that will require fewer steps than the problems you've seen in the homework. Okay, and I've already set the midterm, and there are 4 questions on the midterm, and it's going to cover not just the material since midterm 1, but all of the material from lecture 1 through lecture 21. Okay, so make sure since it's an open note exam, make sure you have all your notes, because even if the question may not necessarily be directly related to material that you've seen that was covered in midterm 1, you may need some of those things. You can't forget, things like what convexity is and results like the maximum of a bunch of convex functions is a convex function, and so on. So you will have those notes in front of you when you take the exam. So you should be able to look it up if you forgot something. Okay. But one thing I didn't test on midterm 1, which I will test on midterm 2, is convergence of iterative algorithms. Okay. So there was no question like that in midterm 1. So, and for that, you might need to go back and look at some results that we derived earlier in the course, early in the course when we talked about convergence of gradient descent. But it should be obvious from the question which notes you need to refer to, if you need to refer to any notes. Okay. So nobody's asking any questions. So either everything is clear or you guys have not started preparing for the exam yet.
How many questions are in the exam?
4 questions. There'll be there'll be something that involves KKT conditions. So make sure you can solve inequality and equality constraint problems using KKT conditions. And something on duality. Okay, and there's something on topic of subgradients, which of course covered in homework 5, and something on convergence of iterative algorithms.
I have two questions.
Yeah.
So the first one is, in general sufficiency condition, the hi of x has to be a affine function, and I don't know the difference between affine and a linear function.
Oh, yeah, what's the difference between affine and linear function? I mean, in order to apply the general sufficiency condition easily, that's when you require it to be affine, and that's because if you have an equality constraint, then that set is going to be convex only when the hi. So you basically want this set to be a convex set. Let's see. Okay, so if you have hi of x equal to 0, okay. So when is the set of x such that hi of x equal to 0? So when is this convex? Huh? So is this thing convex? Well, so if you have if you look at a linear and if hi was convex, would this be necessarily convex? An arbitrary convex function. So, for example, let's take hi of x equal to x squared, okay, which is a convex function. Would the set of let's say let's make it x squared minus 1. Say, with the set of x such that x squared is equal to 1, is this convex?
I don't think so, because -1 and 1 are in the set, but 0 is not.
Right. So this set only keeps the circle, for example, in 2 dimensions, and this is not a convex set, right? So you take a convex combination, say, of this point and this point. You say convex combination of a half, you get this point, which is not inside on this set. So if it's not enough for hi to just be convex, but what happens is that if hi is affine or linear, then it's okay. So what is affine? What's linear, first of all? A linear function is of the form, summation ai xi. Okay. So it's just a linear combination of the xi's. So this is a linear function. What's affine? It's the linear combination plus some constant. Okay. So so basically, a lot of times when we say hi is linear, we really it's a bit of a misnomer, because we actually say that it could be affine. Okay, so some linear combination plus a constant. Okay, so that's how you would see most when you say the constraint is linear, we mean really that hi is affine.
Would this hold for any h of I that was like 1-to-1? So you wouldn't have like these disjoint sets where they could equal 0?
So if you're saying, what if I have multiple hi equal to 0?
I'm saying if you had a function that was 1-to-1, so you wouldn't have like a repeated value. Like you wouldn't have the point where like x squared could equal 1 for 2 different values of x.
Okay.
In that case, that would be a convex set, right?
Not necessarily, again. Right. Let's That's not necessarily the case, although let me try to see if I can come up with an example. So you're saying if I have one-to-one mapping, HI is a one-to-one function, an invertible function, where the setting that equal to 0 would result in a convex set. Not necessarily. I mean, think about. I mean, an equality constraint. Actually, it's really not full, right? It's like the rim of a thing. So anything inside the rim, you can create by taking convex combinations of stuff that's on those.
Oh, gotcha.
So I don't think it's the one-to-one that's the issue here. Okay. Yeah.
Thank you. I just have a last question. So when we use the subgradient descent method, when we approach the point where there is no gradient, we will have a gradient or subgradient that has a range. And which of the value do we choose? Do we choose like arbitrarily, or do we have a method to choose inside the range?
So let's maybe go. Which lecture was that? Lecture 20?
Yeah, I think it was 20 or 21. Let me look at it.
So here, is that what you're talking about? This proof here?
Right. So
you're saying what happens when you get close to? So suppose you're saying you're in a situation where there is no. So you could have. I mean, I can just create something here. So you could have a situation where I have, no subgradient here, but as I get to the minimum, it becomes nice and smooth and I have a gradient there, right?
right.
So here there's no gradient, but here the gradient is 0.
Right.
So what you're saying, what if there's a situation where I go down to the minimum and then the thing is not differentiable there. It might be differentiable elsewhere, but it's not differentiable at the minimum. Right?
Sorry, I was asking for the figure above, right. Which gradient do we choose for the subgradient method?
Yeah, so it doesn't matter which one you choose.
Anything is fine. Okay.
Yeah, that's what the proof says. In fact, it's not in high dimensions. This is what I was maybe I mentioned that in lecture 21 when I talked about with diminishing step size. So basically, you could have some directions, like in this example, you could have some directions that are not descent directions, right? And you're not at the minimum. So the minimum of this function is 0, 0, and you are at 0, 1 in this case. And now at 0, 1, it's not differentiable. So you have this range of possible subgradients, right? This set of subgradients. And if you happen to choose one that is like on the left side, -1, 1, we showed that this is not a descent direction. Okay. So at that point, you'll actually be going away from the minimum. Okay. But that's all right, because what happens is that you get to a new value, and so you can you basically correct for it later. Okay, you can, and these are going to be like very discrete points at which you'll have the gradient not existing, so where you'll have a range of subgradients to consider. And so whenever you hit those points, if you happen to hit those points, then you have to worry about the choice of a subgradient. But otherwise, you will basically have a gradient. And so when away from that point, you might hit a gradient, and then based on the step size you choose, you might go to some other point. That is not an issue anymore. Okay, so that's why when you look at the proof works because of that reason. Right? The convergence proof.
Okay, thank you.
And but you do need to, if you use a constant step size, then you're not guaranteed to hit the minimum. And the reason why you're not guaranteed is because you could be shuffling around because of the subgradients, which are subgradient directions, which are not great. You could be shuttling around, so you don't quite converge to the minimum. And so, and you can't use backtracking. I mean, with some directions, if they're not descent directions, you can't use backtracking to ensure that you're going down to the minimum. So the only option you have is to decrease the step size. Okay, that's exactly what we did here. We used a diminishing step size. And so if you have a diminishing step size, then you choose that step size appropriately in such a way that this condition holds, then you get convergence. And we saw two examples of that. 1 over k and 1 over square root of k. Okay. In which case you either get 1 over log of n rate of convergence or 1 over square root of n convergence, which is still worse than gradient descent, which is 1 over n. Okay, but this is the best you can do. Now, this is actually, speaking of that, if you can apply, even though, when we studied gradient descent, let's see, lecture 6 or 7. So if you remember, when we studied steepest descent, we studied only with fixed step size. Okay, and of course you choose that step size to be between 0 and 2 over L. We showed that we have convergence, right? So every stationary point is going to be a minimum of. Sorry, every limit point of xk is going to be a stationary point of f. And if it's convex, that was lecture 7, I think, when we explored convexity to show that you actually go to the minimum, right? So, so you could apply this method, and maybe but let's go look at lecture 7 as well. So in lecture 7, we exploited convexity, and then we got that we have a rate of 1 over k, right? Fk or fn, f of xn goes to f of x star, rate 1 over n. Here we just use k, I think. Okay, so so how do we get that? So what do we exploit that? So we needed, even in this proof, we needed to use the fact that the step size has to be less than 2 over L. Okay, which you can do. Well, what would you need to know in order to make it less than 2 over L? Yeah. So if you want to choose constant step size, you know that a constant step size works only if it's less than something. And so in order to make it less than something, you have to know the Lipschitz constant. So in many examples that you might encounter in the real world, it may not be unreasonable to assume that the function has Lipschitz gradients, but it may be hard to exactly pinpoint what that Lipschitz gradient parameter is, right? Especially in high dimensions. Okay. So think about trying to use these algorithms for optimizing the parameters of a neural network or something. So you even if you have Lipschitz gradients, you may not know L, in which case you may not be able to set a fixed step size beforehand. So then what can you do? Okay, will you just give up, or do you have an alternative method that might allow you to converge still? Based on what we just studied in lecture 20 and 21. So there's nothing that stops you from using a diminishing step size, even when you have gradients existing and gradients being Lipschitz, right? If you don't know the Lipschitz constant, you can still choose to use a diminishing step size, or you can what's the other method you can use?
The Armyhold rules.
Yeah, Armyhold rule. Yeah, adaptive step size. So you can adapt it at each time step. Okay, but if you don't want to adapt, then you can use some predefined, a rule like 1 over k or 1 over square root of k type behavior, you can set it beforehand, that kind of diminishing step size. So that's something to keep in mind. Although, what would be the issue with the diminishing step size? From a practical viewpoint.
Maybe it would be too slow to converge.
Yeah, you're going to reduce the rate of convergence, and we saw that here, right, in this example with subgradient descent. Okay, so if you choose 1 over k, then your rate of convergence goes down to 1 over log n. So but there's no reason not to use something like an adaptive step size when you know when gradients exist. Okay. It's just that when gradients don't exist and you only have subgradients, and you don't know whether the subgradient direction is really good, like in this example, then you can't use adaptive step size. You can't use Armyhold's rule or backtracking, and so you would use. You may be forced to use a diminishing step size. Okay. So everyone should have submitted your homework 5. So actually, I wanted to say something about some of the problems you saw in homework 5.
Sorry, I have a question.
Yeah.
So if we have convexity for a constraint optimization for the function and the constraints, can we just use the first order condition to say we have a global minimum?
Yeah, but what first order condition are you talking about? KKT?
Yes.
Well, okay. So if you have a convex function and the constraint is closed and convex, right?
Yeah.
Well, strictly speaking, we haven't shown that implies the first order condition. So if you want to be completely formal, you have to use the first order condition. Like let's see, which lecture was it? Lecture 10 maybe, when we talked about before we started talking about KKT. Yeah, this one, right? Yeah.
Mm-hmm.
So basically here, this is the constraint set in this setup was closed and convex, right, and non-empty. Okay, so and if f is convex, then this condition is necessary and sufficient, right? Now this does involve a first order only a first order, just the gradient, right? So this is a first order condition, but how is this related to the first order KKT condition? So strictly speaking, if you verify the first order KKT condition and you get some X star and you want to apply this result, then you have to also establish this, which you can do for most of the examples we've done. Okay.
Okay.
But a better way would be just to go ahead and use either the second order condition or use the general sufficiency condition. In most of the examples that we did, you could use. So if you use the second order sufficiency condition, you can verify that it's actually a minimum, and if it's a unique solution, and that's there's only one minimum basically, and the function is convex, and the constraint set is closed, right? Closed and convex, of course, because to define a convex function, you have to have a convex set. So then, then what you said would be true, that since you know that the minimum has to exist, okay, by the closure, then and you found one candidate for a minimum, you're done. And since it's convex, every local minimum is a global minimum, and there's only one candidate, and that's a global minimum, and you're done.
Okay.
Okay, but since you still require to check that the second order condition holds. So it's not enough just to check the first order condition. You have to check the second order condition holds.
Okay. Yeah. Thanks.
Can I have a question?
The other option, of course, is to just see if the Lagrangian is convex, and then you know that if a Lagrangian is convex, and then the first order condition, first order KKT condition, the X star that you found is a minimum. It gives you a minimum of the Lagrangian, and you can use general sufficiency to conclude the same thing. Okay, so.
Yeah.
So we actually looked at both of those options. But maybe just look at the solution to homework 4 again, just to make sure that we understand that. Where's homework 4? I don't see. I thought I had it here. Maybe I can pick it up from the website. Yeah, so let's see. Maybe this was a good example for that, right? So where so this first example, this is convex, and these constraints are inequality constraints are linear, and these are obviously convex for that reason. So this set is a convex constraint set. And also the Lagrangian, when you take linear combinations of this thing, will be convex, right? And so here we found one candidate for. We found that there's only one candidate for the minimum, this X star and the corresponding mu, and we also checked that you can check easily in this case the second order sufficiency condition is satisfied, and so since it's unique, and further, since F is strictly convex and this constraint set is convex and closed, this is also the global minimum. Okay, and the other way to do it was that if you look at the Lagrangian, this is since this is strictly convex and G1 is convex, the Lagrangian is convex. So X star, because it satisfies gradient of the Lagrangian equal to 0, is a unique minimum of this Lx of mu, and then when based by general sufficiency, that's a global minimum. Okay, so either method will work in most problems. Okay, I think there was one example we did in class for which we could use the general sufficiency condition more easily. That's because the function, I remember. No, we couldn't use the general sufficiency condition because the function wasn't convex. And so I don't remember which lecture that was. Yeah, we had like x1, x2 plus x2, x3, and x1, x3. And so we had to use, we used the second order condition for that. We had to show that, and actually on the set, since it's not a convex function, but you know, y transpose Hessian times y, where for y belonging to v star, v of x star, we could show that condition. And let's see, maybe it's worth reviewing that. So, but in most of the examples, you can use one of these two arguments quite easily. Okay, and both work. Let's see, which, you remember which lecture that was? Was it 12 or 13? Where we talked about that example. No, that's 12. Maybe oh yeah, this is this one. Yeah. Yeah, so this is the function. Yeah, so the in this case the Hessian well is not positive definite or not even PSD, right? But if we check that that if you look at y such that gradient of h1 dot y and gradient of h2 dot y are both 0, and look at only those y's, and look at y transpose the Hessian times y, we showed that that was positive. Okay, so then that establishes that x star is a strict local minimum. And then to see that as a global minimum, we use the coercivity, because we can't use convexity anymore because f is not convex. So then we use the coercivity. Okay, and showed that there exists a minimum, and we found one candidate, and so that must be the minimum. So that was the argument. So this was a little more complicated, but in most examples, your function is going to be convex and the constraint set is going to be convex and closed, and so you can use directly use the second either you know, one of the two methods we just discussed. Right. So I won't make you do something more complicated, especially in an exam. So. Okay, one thing I should mention about the latest homework, because there were a few questions about it. Let's see. So here no, this is not the example I want to talk about. Yeah, I want to talk about this example. Yeah. Okay. So here we found that I should find the dual of this, and actually find the dual is not that difficult, because we know that the dual is a concave function, right? So first order, you know, when if you want to optimize the dual, then it's you already know that it's a you know, concave function, and negative of it's a convex function. And then to find, in this case, the original function has a Lagrangian. This Lagrangian Lx mu is convex. So in order to do this optimization, this is also easy. Just use this first order conditions. Okay, and substituting, we get this thing. And you can easily see this is a quadratic again. And if you take the negative of this, you can easily see that it's a convex function, right? It's mu1. This becomes positive. This becomes positive, and so on. So this becomes a negative. This is a convex function. So the negative of this I call B mu. But the only thing here, a little bit in terms of notation, that might confuse you, because now when you are trying to maximize d mu or minimize the negative of d mu, okay, this is again a constraint optimization problem. So whenever you have inequality constraints here in the original problem, if you have inequality constraints, then the dual optimization problem will also involve inequality constraints, because mu has to be, but these are much simpler inequality constraints to deal with. All they're saying that each of the mu's has to be positive or non-negative. Okay, and so, but you still have to consider 4 cases to solve this, and since now this could be confusing to some of you. Okay, so now the x is replaced by mu. Mu is the variable now of your optimization. Okay, and if you have both inequality and equality constraints, then you would end up with a function like for example, I'm just making this up. It may not necessarily be a good example, but suppose I replace this constraint with an equality constraint, right? Then I would only have this. This is the only inequality constraint, right? So then, when I solve for my, of course, this solution is no longer going to be valid. It'll be something else. But basically, I'll have a solution x star, and then there'll be a corresponding lambda and mu, right? And so just mu. In this case, there were just two mu's, mu1 and mu2. But I might, if I have an equality constraint here, inequality here, I'll have a lambda mu. Okay, and then now d will become d lambda mu here. Okay, but the lambda parameter, okay, is allowed to be anything, can be any real number. But mu can only be positive and not negative. Okay, so whenever you have inequality constraints here and inequality constraint here, then you will end up with in the dual optimization problem, you'll have some inequality constraint. So it becomes a constraint problem. If you only had equality constraints in this problem, then your dual d lambda, or in this case b lambda, the negative d lambda, will be an unconstrained problem. Okay, so so since this is constrained, since you have these inequality constraints here, you have to deal with them, and so you have to consider cases. Okay, and use a different symbol, right? To avoid confusion, use a different symbol like nu for the Lagrange parameters corresponding to this optimization problem. Okay. Another thing you can do if you at an exam situation or something like that, you can change the variable, right? When you're solving the dual, change the variable name to something else like y or something. Okay, so that it's less confusing. Okay, so instead of writing it this way, write it as minimize y bigger than 0 and b of y. Okay, and then introduce a Lagrangian L of y nu, use a different parameter other than mu, just again to be safe, and write that as by minus nu nu1 y1 minus nu2 y2. Okay, so you could do that if in case, because if you're used to thinking of mu as a Lagrange parameter, and then suddenly in the dual problem it becomes a variable, some of you might get confused. I get confused too sometimes when I do that. So okay, so That's one thing just to keep in mind, because I will make you do something like this in the exam. Okay, I'll make you solve a dual problem.
So for this problem, why do we need to solve the dual problem?
Oh, I want you. I'm asking you to solve it. I'm saying just to verify that strong duality holds.
Oh, so if I plug in the x star and mu star and find that the minimum of fx equal to the maximum of du, will that why won't that be sufficient to
How do you
verify?
find the maximum of d mu? You have to solve that optimization problem, right?
Because in problem 3, the x star and mu star are given.
Yeah, but that mu star, unless you know that strong duality holds, that mu star may not be the maximizer of D. Unless you know beforehand that strong duality holds. But I'm asking you to find the dual from first principles by doing the optimization. So you find the dual function first, and then you have to optimize d mu over mu separately. Think of it as a separate optimization problem. Okay.
Okay, I see.
Yeah, otherwise it's cheating. Yeah. Yeah, it turns out at the end you will verify that the mu that you get is the mu that you found earlier. The mu star that optimizes d mu is indeed 8,0. But you have to prove that in this problem. That was the whole point of this problem. Okay.
I have a question. So if for some mu we show that d mu is equal to minimum of f, isn't it enough to say that this mu is mu star?
Some minimum of f?
Yes, so for example,
maximum of d is what you want, right?
Yes, so for example, if we say that mu is equal to 8 and 0, and if we calculate d and we see that d is equal to 1, and if we calculate the f at x star, it is also equal to 1. So if now we are saying that d is equal to f, so this mu is equal to mu star. And we don't need to go through all these steps.
Yeah, but that was not the point of this exercise. That only the only reason why that works is because for this example, all the latest conditions hold. And yeah, so I'd really like you to go through these steps, just to make sure you can solve the dual, because a lot of times, you might end up solving the dual of an optimization problem even when latest conditions don't hold, and even when strong duality doesn't hold. Okay, because the dual problem turns out to be simpler to solve because it's always a convex problem, and then there'll be a gap in that case. Okay, so I mean, the reason why it works in this case is because strong duality holds, right? That's why it works.
Yeah, I mean, so to solve this problem, isn't it enough to say that for this mu, d is equal to f, so that's the mu star, and we don't need to go through all these steps? Because we just need to say that to show that the strong duality hold. So we show that for this mu, d is equal to f, so that's the showing that this holds.
Yeah, but that was not the point of this exercise. If that's what you're doing.
Yeah, I see.
Yeah.
Can I have questions?
Yeah.
So in this problem, can we use the Slater conditions to verify if the strong duality holds?
Yeah, but yes.
Yeah,
but
I know.
But that was not the point of this exercise, right? Otherwise, I wouldn't have made you do this, right? I wanted you to solve the dual. I wanted you to solve the dual. That was the point of the problem. Just so that you know that you verify what you learned, because we didn't actually prove strong duality holds under the general Slater condition. We proved it in a special case, and this problem actually happens to be covered by that special case that we
yeah. So yeah, my question is like how to use the Slater conditions to verify if the strong duality holds or not without solving the dual, like for all the problems, not for these specific problems.
Oh, I see. So yeah, but then you have to actually go over the proof. Like no, when we proved strong duality holds under those convexity conditions that we discussed, we actually had to go through all the steps, right, to show that it holds. And so you can modify the conditions and under. So Slater's conditions are not the only conditions under which strong duality holds. You can show it under other conditions as well. Yeah, if that's what you're asking. But you have to prove it. You have to go through a similar proof as the one we did in class for Slater's condition. Or the strong version of Slater's condition. So anyone remember which lecture that was? We talked about duality. Was it 18? Not this one, right? Which anyone remember? Which
I think
one?
it's lecture 18. Lecture 18.
18?
18, yeah.
Here. Yeah, so here, what we showed was if the F is convex, HIs are affine, G's are convex, then strong duality holds actually. And also that lambda star and mu star maximize d lambda mu. Yeah. So so if you can, but the actual Slater's condition. So this okay, we proved it under the strong condition that this constraint set S was equal to Rn, but there are situations, example, when the function's domain is not all of Rn, right? When this may not hold, so the S could be some subset of Rn. Okay, so our proof, where we exploited all the properties, actually, the fact that S is equal to Rn, the convexity, everything we used to prove this result, right? But then I mentioned later that where was that? That the Slater's condition is actually a slight generalization of that. So, and it's a non-trivial generalization, by the way, in the sense that if S is a subset of Rn, not equal to Rn, and then you need this relative interior condition. Okay. And this proof is a lot more complicated than the proof I gave when S is equal to Rn. Okay. But this is not the only condition. This is not the only condition under which strong duality holds. There are other conditions. And the book, I don't think Bertzicker's book has all of the possible conditions. But if you look at the book by Boyd and Van der Burgi, okay, they have a lot of discussion on this issue. Okay, but the point of this exercise, homework 5, was for you to actually solve the dual and show that indeed, you know, the strong duality holds. And indeed, when you solve the dual optimization problem, the lambda that you obtain is the lambda star that you obtained from the original problem. Okay, there's a double check. Okay, there was that.
Professor, I had one more quick question about this problem.
Yeah.
So you're deriving the dual in line 19 there by essentially solving for x1 and x2. Since we're given what x star is, wouldn't we be able to just plug that into the Lagrangian?
No. This is actually the x star for an arbitrary mu1 and mu2. Yeah, so this is different, right? So if, for example, okay, I can't see it here, but if you, let's see. So yeah, so the x star, yeah, I gave it to you. Yeah, the x star for the original problem, this optimization problem. Let me erase all of this. So the x star for this problem is 3 minus 1. Okay, and that was correspond to the Lagrange multiplier 8, 0. What we're solving here for the dual is an x star that minimizes L x mu for an arbitrary mu1 and mu2. Again, that's going to be a function of mu1 and mu2.
Okay, so the only reason
so you would have that function, and that's how you get a function of mu here. Okay.
Okay, thank you.
I also had a quick question about this problem.
Mm-hmm.
When we're going to the dual function and we're plugging in the x1 and x2, why are the x1 squared and x2 squared negatives?
Oh, it just comes from this part, right? So if you look at x1 squared, so that will be this thing squared, right? But then if you take the terms involving x1 and plug that in, so that's a mu1 plus mu2 minus 14, and x1 is minus of that. So this one is actually minus of x1 squared times 2. Okay, and that's how you get this. So this turns out to be the dominant term, and this is a negative.
Okay, thank you.
So this guy essentially subtracts out from here, and you get that.
Can I have a questions about the lecture 21?
Yeah.
Yes, in the last page. In the last page.
Yeah. Yeah.
Yes. This one. So I wonder on the last slide, how can we end up with the term of log n over square of n? The last slide.
This one here.
Yes. How can we end up with that terms?
Yeah, because here we have this guy. This guy is log n, and this guy is square root of n, right? Summation alpha k is square root of n. Summation alpha squared is less than log n, order log n. So this is order log n. This is just a constant, and this is order square root of n. Lower bounded. So up 1 over that is upper bounded by.
Oh, okay. I see it. Yeah. Thank you.
I mean, 1 over square root of n. Sorry, yeah. That's why I had to make sure, to be technically correct, I had to make sure that this guy is upper bounded by something constant times log n, and this guy is lower bounded by something that's constant times square root of n, which is what we showed here.
So do we need to remember like the sum of 1 over k is less than log of n in the exam or something?
No. But you would need to know something like, what does it mean for a sequence to converge? Right? If I say a sequence of numbers converges to something, converges to 1, right? If a sequence xk converges to 1, what does that mean? Right? What does that mean? Anyone? If I say xk, and we use this a lot in the course, but if I say a sequence xk limit k goes to infinity, xk equal to 1. That means I can make my xk as close to 1 as I want if I make k large, right? So it means that given any epsilon bigger than 0, then I could make my xk minus 1 absolute value less than epsilon. I can make it as close as I want. So there exists, say, some number n, such that this holds for all k bigger than n. Right, so that's what, or you can put equalities if you want. Very well. So you would need to use this kind of information. This is the kind of thing I want you to remember. I don't want you to necessarily want you to remember that sum of 1 over k is log n, but I would want you to know what the definition, what it means for something to converge. Okay.
Are we allowed to print off homework solutions for the exam?
Oh, yes. Yeah, I should have mentioned that. Yeah, that's really can be considered part of your notes. I don't want to make it open textbook because a lot of you don't have hard copies of the textbook, so it wouldn't be fair. So that's why I made it only open notes. Yeah, but your own homework solutions and my homework solutions really can be considered part of the notes.
So when you show the subdifferential of like when you show a claim about the subdifferential in some set, you verify the converse.
I don't expect you to do that in an exam, because sometimes in some examples constructing the converse is hard. I mean, it's a little more involved, not necessarily hard, but a little more involved. So in the exam, if I do have a question about subgradients, but I specifically ask you to only go one way. In other words, if G belongs to the set of the set of subgradients at that point, show that that G is indeed a subgradient. It satisfies the definition.
Thank you.
Anything outside that set, proving that it's not a subgradient, I don't care if you show it or not. If you want to show it, you can. Yeah, I think that's why I changed the wording in homework 5 as well. Let's see. Yeah. This problem, not just, yeah, this problem, subgradient in 2 dimensions. Here is that all you need to show is that any A and B in this set is subgradient for F. But anything outside the set, it's actually, in this case, it's quite easy to show that anything outside the set is not going to satisfy the condition for a subgradient. But yeah, but there are some examples where it's a little more involved to show that something that's outside the set. And in practice, when you use this stuff, you know, you would essentially, if you can guess a good enough set, right? It may not be the entire thing, some subset that is contained within the subdifferential. At that point, you're okay, because you're going to choose that some candidate from that set in your subgradient algorithm. Okay, and the same here. I changed the wording of this problem as well to show that for every solution x lambda, this is subgradient. But to show that something that's not outside of this is not a subgradient is a little more involved here. And that's the same with this example, this problem. To show to go the other way, that that anything that cannot be written as the sum of these the subgradients of f1, f2 cannot be a subgradient of f1 plus f2. That in fact, and this is actually a lot more complicated in this case. You need results that go beyond what we've covered in 490, which is why I just asked you to go one way here. But for these, for 1 and 3, it was very easy to go both ways from the definition. So again, let me emphasize, in the exam, if I ask you to solve the dual, because I want you to go through those steps of solving the dual. And okay, don't say, okay, I'm just going to verify that lambda star satisfies the strong duality condition, so I've solved the dual. Okay, that wouldn't be the point of the problem. Okay, any other questions? All right, so we can, I guess we can end. And oh, I should mention that, you know, I think for midterm 1, I made it an hour and a half, but then CBTF really gives you a 1 hour and 50-minute slot. You know, they don't have an hour and a half slot. So this exam, you know, I decided, you know, I'm just going to give you an hour and 50 minutes, right? It's just an hour and a half. So you can take the full hour and 50 minutes, and then I think you'll have some time after you finish the exam to upload onto Gradescope. So I'll make sure there's enough of a window after the hour and 50 minutes. So in case you have any glitches with uploading, so we'll give you enough time to do that. And if you have any problems with uploading, you can always contact the CBDF proctor and let them know. And as long as you register with them and figure out together with them how to upload, you should be okay. I don't think anyone really had a problem last time, so should be okay. All right. Okay, good luck then. And oh, and Thursday we're not going to have a class, as I mentioned. Okay, so if you guys need to go early for Thanksgiving break, and you don't have anything else, anything else on Thursday or Friday, you can do that. And so then I guess I won't see you again until after the break, right? So I think we have 3 lectures after the break. So my plan for the lectures after the break are going to be more on material that I'm not going to really be able to test you in a homework or an exam. So think of this midterm 2 as really something like a final exam, because it's comprehensive. It's all the material we have covered until lecture 21. So what I'll focus on are a little more advanced topics, just to give you a flavor for some of those kinds of topics. Might talk about things like stochastic gradient descent, which is what is used in a lot of applications these days, and in proximal algorithms, and maybe talk about a little more interesting example of optimization methods in the context of machine learning, something like support vector machines or something like that. So I'll plan out something to discuss in those 3 lectures, but it'll be mostly for your benefit. It's you're not going to be tested, so it's think of them as seminars, right? That might be useful to you at some point in your research. Okay, so good luck on the exam, and have a good break after that.
Thanks, you too.
Thank you. See you.
Yeah.